Cement producers all over the world are realizing the benefits of burning waste fuels. This is helping not only to preserve scenic Norway, which you see here, but burning waste fuels can have substantial economic benefits for cement producers as well. F.L. Smith is pleased to offer an innovative technology for burning bulk waste, such as whole automobile tires. This technology is specifically designed for the calciner area of modern cement plants, where, until now, it has not been possible to successfully burn large amounts of whole tires. Successful combustion in a modern calciner requires adequate retention time and temperature. However, successful combustion also calls for the size of the fuel to be small enough to burn in suspension. The problem is that many types of waste simply cannot be economically ground or shredded to the fineness required to burn in suspension. Chipping tires, for example, is very expensive. Fortunately, F.L. Smith has developed an innovative solution to this problem. The invention is a disc reactor placed in parallel to the kiln riser duct, which is simply able to control the two primary requirements for complete combustion. The reactor, which we call the Hotdisc, continuously satisfies both time and temperature, making it possible to burn bulk waste in the calciner that otherwise would not be possible. In fact, the invention makes it possible to substitute upwards of 70% of the calciner fuel with bulk waste. The device may be installed as part of any new calciner, as well as many existing calciners. To do so, we simply connect the tertiary air duct to the roof of the disc and add waste. The waste simply replaces a substantial portion of the conventional fuel that is normally fired into the kiln riser duct for a low NOx system such as the one you see here. A meal split then is used to control the temperature within the disc. Now, let's take a closer look at the invention. The disc reactor consists of a turntable onto which the waste materials are dropped. As the waste is exposed to the hot tertiary air, it burns out on its way around the rotating disc. As shown, tires burn rapidly when exposed to tertiary air from the clinker cooler. The speed of the disc is simply adjusted to the specific type of waste fuel being processed to assure complete burnout. Then, it's simply a matter of throwing another log, or tire, onto the fire. The refractory-lined reactor is divided by a wall. The wall acts as a scraper. The wall also separates the waste inlet from the ash outlet, as shown here. As previously mentioned, the tertiary air from the cooler is connected to the roof of the disc. This supplies all of the combustion air needed for the calciner. As such, the disc always operates under full oxidizing conditions, thereby eliminating the risk of explosions. Importantly, this is a combustor, not a gasifier. Time and temperature are easy to control. There is absolutely no need for water, a burner, or flares to control the combustion process. Let's see why by looking at the means of temperature control. As shown, the temperature inside the reactor is controlled by the endothermic reaction of raw meal calcination. This is accomplished by adjusting the splitter gate position from the second lowest preheater stage onto the disc. The temperature is controlled at 1000 to 1200 degrees Celsius. Now, let's take an actual look in through the tire feed chute to see the temperature being controlled within the disc reactor. In this video, you can see preheated raw meal being added from the far right. This meal is from stage 4 of this 5-stage preheater installation. At 1000 degrees Celsius, the raw meal will be flash calcined and thereby provide a very stable means for temperature control. Here we see the bed of the calcined raw meal on the table near the outlet of the disc reactor. The disc reactor typically adds only 10 millimeters water gauge to the overall pressure drop of the pyro system. As shown, the low gas velocities effectively minimize the meal and ash from being swept off the disc. This is a tribute to the low gas velocities present within the chamber. As mentioned, the disc reactor is uniquely flexible to handle all kinds of waste, whether they be shredded or fired in bulk. Here we see whole tires being introduced to the disc reactor. Because the speed of the disc is variable from 1 to 4 revolutions per hour, the best possible combustion can be assured even for the most difficult to burn waste materials. Therefore, concerns over the possibility for reducing conditions are completely controllable. Importantly, it is an all-in-one system for both combustion and ash disposal. It has all the advantages of a separate combustion chamber for controlling time and temperature, while still being completely integral in terms of ash disposal. As shown, the waste rotates on the disc for approximately 3/4 of a revolution, after which the residuals are scraped off into the kiln riser duct. In this way, the residuals, such as steel belts from tires, are taken up by the kiln charge without the need, problem, or expense of a separate ash handling system. A side benefit is that this ash replaces a portion of the raw materials processed by the kiln, thereby saving natural resources. Calcined raw meal is carried up to the bottom stage cyclone and the ash falls down into the kiln. The disc exit is simply connected to the kiln riser duct at the entrance to the calciner as shown in the following sequence. For driving the disc, a ring gear and a pair of motors are provided with frequency drive as shown here. This enables the speed of the disc to be varied and therefore the retention time of the waste material on the disc. Of course, different types of waste require different retention times. A retention time for both shredded and whole tires of 15 minutes has proven to be typical. 30 minutes are typically needed for processing lime sludge, and upwards of 45 minutes are typically needed for processing telephone poles. In the following sequence, we will take a walk around the first commercial installation of the disc reactor. First, moving upwards from the rotating table, we see the tertiary air duct. It is connected to the roof of the disc reactor as shown here. Next, we can see the splitter gate dividing stage 4 material between the disc reactor and the calciner. And finally, moving downwards on the calciner, we see the coal pipe connection to the kiln riser duct. As with all calciner kilns, the overall temperature control is made in the traditional manner by maintaining a constant temperature for the calciner exhaust gases. This ensures the consistency of calcination. Conventional fuels are simply fired into the calciner to make up the remainder of the required heat input as needed to maintain a constant calciner exit temperature. It has been proven that a 70-30 split of calciner fuel between the upper and lower positions is possible. In conclusion, A new invention by F.L. Smith provides an innovative solution to waste utilization. As a result of this invention, it is now possible to substitute upwards of 70% of the calciner fuel with solid waste in bulk form. The benefits are obvious: reduced operating costs, an all-in-one system for both combustion and ash disposal, fewer landfills, improved capability to meet NOx and CO2 requirements, and savings of our natural resources for future generations.